Welcome to The Explainer. Today, we're diving into what's honestly a pretty thrilling tech detective story, and it's pulled straight from Perplexity AI's engineering logs. We're looking at their recent move to completely rebuild their Unigram tokenizer from the ground up using Rust. It's a move that massively accelerated their system. Now, if you build or run AI models, you already know that speed is absolutely everything. But where exactly does a system slow down? Well, the answer might actually surprise you. So let's dive right in. When we talk about the cost and the latency of large language model inference, the conversation almost always revolves around the GPU, right? We're constantly hearing about KV caches, attention kernels, expert routing, the whole shebang. It's incredibly common to just assume that if your AI application is running slow, it's because the GPU compute is bogged down. But we have to ask, is the GPU always the bottleneck? The answer to that is a definitive no. And this brilliantly illustrates exactly why context matters so much. Because while massive frontier transformers are absolutely GPU-bound, smaller models, things like embedding models, classifiers, and re-rankers, they tell a completely different story. These models are 2 to 3 orders of magnitude smaller. For them, the GPU work often finishes in literally single-digit milliseconds. But here's the catch. Every single input still has to pass through CPU-side tokenization first. So when you're processing large batch sizes, that CPU tokenization suddenly balloons. It becomes this massive hidden drag on your total request latency. To understand exactly how Perplexity solved this, we're going to follow a clear roadmap. 1. The hidden inference bottleneck. 2. How Unigram tokenization fails. 3. Establishing a faster baseline. 4. 3 high-speed optimizations. And 5. The final benchmark results.
Let's start with part 1, the hidden inference bottleneck.
We have a really clear contrast here. On one side, you have massive frontier transformers where the GPU compute completely dominates the time. On the other side, you have the re-rankers and classifiers. Perplexity's main target here was XLM Roberta, which is a model with a massive 250,000 token Unigram vocabulary trained with SentencePiece. Fine-tuned Roberta encoders are heavily used in production for ranking and retrieval. Just imagine a re-ranker scoring hundreds of candidate documents for a single search request. The GPU tears through that small model in milliseconds, but the CPU, it gets completely stuck in the mud trying to tokenize all those documents. So we have to figure out, what is the CPU actually doing that's taking so long? And that brings us right to Unigram tokenization. First introduced back in 2018, it frames text segmentation as a most probable path problem. Basically, each token in the vocabulary has a learned probability score, and the tokenizer has to pick the segmentation path where those scores sum up to the highest overall value. To find that path, it uses what's called the Viterbi algorithm. It's actually a dynamic programming technique dating all the way back to 1967. Think of it like trying to find the absolute best, most efficient path through a giant, complex maze. The CPU has this inner loop that constantly walks a vocabulary trie, which is essentially a prefix tree structure. On a 16,000 token input, that inner loop executes hundreds of thousands of transitions. It is an incredibly hot path for the CPU to handle.
Which leads us to part 2, how un-Unigram tokenization fails. So let's break down the actual suspects in our detective story. Perplexity used the default Hugging Face tokenizer's crate in Rust as their reference point. And when they really analyzed it, they found 3 major bottlenecks. First, memory allocation per match. Second, constant pointer chasing at every single byte step, which caused severe dependent load latency. And third, L2 cache thrashing. The standard implementation was constantly allocating fresh tables and buffers. At 16,000 tokens, the L2 cache miss rate just skyrocketed, hitting 50%. The CPU was basically spending all of its time fetching data from slower memory instead of actually doing the math. Let's just pause and highlight exactly how bad that first bottleneck was. 7,295. That is the staggering number of memory allocations the default Hugging Face tokenizer was making for an input of a mere 514 tokens. It was allocating about 2 kilobytes and doing 18 separate memory allocations per single token. When you scale that up to longer inputs, those cumulative memory tasks completely overflow the CPU's L2 cache. The system was essentially choking on its own memory management. Moving on to part 3, establishing a faster baseline. 0. Literally 0. This is a real wow moment in the engineering logs. Perplexity achieved 0 steady-state heap allocations. How did they do it? Honestly, just by cleaning up the code. They kept the exact same hash map structure as the reference, but completely stopped creating new memory for every call. Instead, they just reused a caller-owned scratch struct across calls, and they stored token IDs directly in the try notes to remove secondary lookups entirely. And the result of just that cleanup? By simply removing the unnecessary work and hitting that zero allocation baseline, the median latency, the P50 latency, was cut from 326 microseconds down to 155 microseconds. They more than half the latency just by practicing good memory hygiene. But a latency of 155 microseconds still wasn't fast enough. The CPU is still stuck doing all those hash map pointer chases, so it was time for the heavy lifting. Part 4, 3 high-speed optimizations. So they tackled the core problem in 3 distinct, highly technical steps. Step 1, they implemented a double array try. Step 2, they used bitmap and inline packing. And step 3, they optimized memory at the operating system level using huge pages. Let's break these down one by one because it's super cool to see exactly how they squeezed every last ounce of performance out of the CPU. Okay, step 1 was the double array try. The old Hugging Face method used a hash map at every single node. That requires hash computations and multiple pointer chases just to move one tiny byte forward. Perplexity ripped that out completely. They replaced it with 2 flat integer arrays, a base array and a check array. Suddenly, a lookup became incredibly simple. You just take the base, add the byte, and verify the check. That's it. 2 array reads, 1 addition, 1 comparison. No hashing at all, no pointer chasing. Almost overnight, the entire 250,000 token vocabulary fit right into about 9 megabytes of contiguous memory, and the hot working set easily fit inside the CPU's L2 cache. The result? Latency plummeted again from 155 microseconds down to just 68. But they absolutely did not stop there. Step 2 was cache line packing. See, the double array try still required 2 dependent array loads per step. The Perplexity engineers thought, hey, what if we can grab everything we need in one single hardware motion? So they replaced the check array with a highly efficient 32-byte bitmap. Then they took that bitmap, the base offset, the token ID, and the score, and packed them all perfectly into a single 64-byte chunk. Now, why 64 bytes? Because that exactly matches the width of a standard CPU cache line. Think of it like packing a suitcase for a trip. If you pack it perfectly, everything you need for the day is right there on top. One step through the try now loads exactly 1 cache line. This optimization alone dropped L2 cache accesses from 4,600 down to 1,800 per encode. Step 3 takes us down to the OS level. By expanding the data to pack it perfectly into those cache lines, the total try size grew to 50 megabytes. On a standard Linux system, which uses 4 kilobyte memory pages, 50 megabytes spans 12,000 virtual pages. The CPU's translation look-aside buffer, the TLB, which is essentially a quick index for memory, can only hold about 96 entries on their Intel Sapphire Rapids chips. As you can guess, this caused massive TLB misses. To fix this, Perplexity switched to 2 megabyte huge pages. Now, that exact same 50 megabytes only requires 25 pages. It fits perfectly within the CPU's limits, totally eliminating thousands of wasted cycles that were spent simply walking page tables. And finally, part 5, the final benchmark results. All of this incredible engineering work paid off beautifully. Look at this. For a 514 token input, the original Hugging Face crate took 349 microseconds. The C++ standard SentencePiece took 128 microseconds. But Perplexity's new, fully optimized Rust Unigram tokenizer, it took just 63 microseconds. On top of that, the actual number of instructions the CPU had to process per encode fell by a massive 3.5 times. And here is the truly crucial point, how this translates to production impact. Because this wasn't just a fun lab experiment. In Perplexity's actual real-world production inference stack, this new tokenizer reduced CPU utilization by 5 to 6 times. It shaved double-digit milliseconds off total re-rank latency, and amazingly, it achieved all of this while remaining completely token exact against the reference. That meant the AI models didn't have to be retrained at all. Plus, they easily parallelized it across CPU cores using the Rust Rayon library. A total win. Before we wrap up, I've got to share this one fascinating detail from the source material. Perplexity noted that a lot of developers try to get around slow Rust tokenization speeds by just using off-the-shelf Rust wrapper creates around native C and C++ libraries, like SentencePiece. But Perplexity found that those wrappers actually add a 1.6 to 1.9x latency overhead just from the wrapping itself. It's a pretty stark warning for developers about the hidden costs of taking the easy route and using generic wrapper crates instead of writing native implementations. Which brings us to a final thought. Perplexity took what seemed like a boring, totally solved problem, text tokenization and proved that it was secretly eating up compute resources. By going way back to first principles and respecting the hardware cache lines and memory pages, they unlocked a 5x speedup. It really makes you wonder, doesn't it? What other hidden bottlenecks are lurking right now in the standard AI infrastructure we use every single day, just waiting to be optimized? Definitely keep that in mind next time you're profiling your own systems. Thanks so much for joining me for this explainer, and keep learning.